We're going to take a look at measurement and significant digits in this video episode. Significant digits is what goes through proper rounding, which is something that's an expectation that you know how to do for the AP exam based on how you process collected data. Now, significant digits are determined by the device that was used to make a measurement when collecting data. Digits are also determined by the mathematical manipulation or type of calculation you do with the data that's collected. Adding and subtracting is one type of manipulation that can influence the number of digits that one has. Also, multiplying and dividing can influence the number of digits one has that are considered significant when collecting data. Now, when taking a measurement, data is recorded to one place past whatever the gradations are that are marked on the device, and that's the proper way to read a device and to collect data. For example, in this graduated cylinder, we can see that the gradations are marked in the ones. We can clearly see here 21, 22, 23 marked on the device. It would be proper then with this device, since the gradations are in the ones, we record the data by estimating to the tenths position. Now we can see here the bottom of the meniscus is between 25 and 26. What we do then is we estimate one place past the gradations to the tenths position, and this will be recorded as approximately 26.8 milliliters. In this graduated cylinder, we can see the gradations are in tenths. So what we'll do is estimate one place past the gradations. In this case, we proper record our data to the hundredths place. And what we record this as 2.67 milliliters, with the 7 being an estimated digit. Now next we'll take a look at how do we determine how many significant digits are in a number that we're manipulating. Our first guideline is that all non-zero numbers are considered significant digits. And for example, this number 5.4, the 5 and the 4 are non-zero numbers, both count as significant digits. We'd say this number has 2 significant digits. Whereas the number 182.1 has a 1, an 8, a 2, and a 1 that are all non-zero numbers, we'd say this number has 4 significant digits. Our second guideline is that all sandwiched zeros count as significant digits. For example, 507 has a 0 sandwiched between the non-zero 5 and 7. All 3 digits count, so we'd say this has 3 significant digits. 0.7001 has 2 zeros sandwiched by the 7 and the 1 non-zero numbers, and we'd say this number has 4 significant digits. The next guideline is that all trailing zeros, this being zeros that are to the right of the decimal and to the right of a non-zero number, these trailing zeros always count as significant digits. For example, this number 0.2400 has zeros that are to the right of the decimal and they're to the right of a non-zero number. All the numbers would count, and we'd say this number has 4 significant digits. The 2, the 4, and both zeros count. This number, the sandwich zero, would count, and this last zero, because it's to the right of the decimal and to the right of a non-zero number, that'd be a 0 that counts. And this number would be identified as having 4 significant digits. The 6, the 0, the 9, and the 0 all count. Our next guideline is something known as leading zeros. These are zeros that are placeholders and disappear when switching to scientific notation. These zeros do not count as significant digits. This number 0.00241 would be an example of this. Let's convert this to scientific notation. When switching to scientific notation, these leading zeros disappear and we have the number now 2.41 times 10 to the negative third. We would identify this number 2.41 as having 3 digits, where the leading digits do not count as significant digits. This number has both leading digits, the zeros that will disappear when putting in scientific notation that won't count, and also a trailing zero that's to the right of the decimal and to the right of a non-zero number that will count as a digit. Putting in scientific notation, we have 5.80 times 10 to the negative 3, and we'd say this number has 3 significant digits. Then our last guideline is there's some zeros that whether they're significant or not depends on the device that's actually used to make the measurement. Now in this circumstance, let's say an individual gets onto a large scale, and we notice that for this scale, the gradations are in the thousands. recording the data to one place past the gradations, we would estimate to the hundredths position and we'd record this weight as 200 pounds. Now the 2 for the 200 is estimated, but the zeros, we have absolutely no idea what we have in the tens or ones position because the gradations on the device do not allow us to record such data. The zeros that we don't know what they are would not count as digits, so we would say that this number has only one digit in it, the 2. Now a chemist would communicate that this number has only one digit and two means, one of which, put it in scientific notation, we'd write this as 2 times 10 to the 2 pounds, which would communicate these zeros are non-significant and we have only one significant digit for our measurement. A second means is to write the number as 200 with no dot or decimal point located at the end of the second zero. By not having a dot there, that communicates that both zeros here are non-significant and we have only one significant digit in the number. Now merely switching the device can change the number of significant digits. In this circumstance, we have a new scale that the the gradations are in the tens position. So for this device, we can estimate and record our data to the ones position. And as in the previous example, we're going to record this, we're going to say 200 pounds. However, in this one, because the gradations are in the tens, that means that this zero is a measured number, because we can see it's right on the 200. And then we also have that our last digit is estimated because the gradations are in the tens. So in this case, both of these zeros would count as significant digits. We can write the number in scientific notation as 2.00 times 10 to the 2 pounds, indicating that both zeros count. We'd say this number has 3 digits. The second strategy is after the second zero here is to include the decimal point. By putting in this dot, that communicates that this has zeros that count as significant digits. So the dot written here would communicate that the zeros count. We'd say that this number contains 3 significant digits. Next, let's take a look at how calculations can influence the number of significant digits we have. Underlying concept is that a calculation may not create more precision than the measured data provides. So let's say we're going to add together these three numbers, 6.5, 4.3264, and 12.01. Adding them together, we'd have 22.8364. However, the number 6.5 does not have any measured data in the hundredths, thousandths, or 10,000ths position. Consequently, when we go to adjust our final answer, the final answer cannot have anything in the hundredths, thousandths, or 10,000ths position. The collected data limits us to express this answer only one place past the decimal, and so the answer, the proper answer, would be 22.8 rather than the 22.8364. We'd round this to 22.8. So the guideline here is we adjust to the least number of places past the decimal in the data that's being added or subtracted. In this case, the 6.5 had only one place past the decimal, so the final answer could only go to one place past the decimal. When we multiply and divide, the guideline is slightly different than it is for adding and subtracting. The guideline for multiplying and dividing, so when doing the calculation, we'll round the answer such that the answer has the same number of digits as the number used in the calculation that has the fewest number of significant digits. So we multiply the numbers 3.582 times 0.68. And the answer we have is 2.43576 is what we would see on the calculator display. We need to identify the digits in the numbers used in the calculation. 3.582 has 4 digits, 0.68 has 2 digits. 2 digits is the lesser number of digits in the calculation, so we have to round this answer so that it reflects 2 digits in the final version. We round to 2 digits and our answer for this calculation would be 2.4.